Hello student, good morning. I am Dr.A.K Sinha, Professor of Chemistry. Now I am going to discuss enthalpy of atomization. Last class I have discussed standard enthalpy of combustion. Now I am going to discuss enthalpy of atomization. And its symbol is delta small a. Down you write delta and down you write small a, H, enthalpy of atomization. What is this? Then you can understand by the example. H2 gas, when it will convert to atom, H2 will give 2H gas G, and it will liberate it will absorb when H2 bond will break, and it will give 2H in gaseous state. Both are in gaseous. H2 is gas already, and when it will break it will give 2H, 2 atom of H gas. Okay. And at that time it required 435.0 kilojoule per mole. Then this heat requirement, heat absorbed 435 kilojoule per mole. Then this 435 kilojoule heat, that is called heat or enthalpy of atomization. Okay. Then here H atoms are formed by breaking HH bonds in a dihydrogen. Dihydrogen means H2. The breaking of HH bonds in dihydrogen. This heat is required, or heat is absorbed. Generally in breaking heat is required. The enthalpy change in this process is known as enthalpy of atomization. The enthalpy change means heat change. The enthalpy change in this process is known as enthalpy of atomization. It is the enthalpy change on breaking 1 mole of bonds completely to obtain atoms in the gas phase. This is the main things. It is the enthalpy change on breaking 1 mole of bonds completely to obtain atoms in the gas phase. Here 1 mole means always you understand this is the big you can say molecule, big mole. This mole means always you understand that this mole contains Avogadro number. You have heard Avogadro number, I already taught 6.02 to 10 to the power 23 particles, maybe atom, maybe molecules, maybe ions, maybe electron, maybe proton, maybe neutron, anything in this number, that is called Avogadro number. Then this in 1 mole, this number of particles will be present. Correct? Big number. Then H2 means not that 1 mole, I am telling you H2 means only 1 H is not like that. This number, Avogadro number, that molecules are present in 1 mole. And then many bonds are there, HH bond. In 1 molecule, 1 bond is there, HH. Then like that, in 1 mole, this Avogadro number, very big number, that you can say number of bonds may be present. then all bond has to break. Then energy involved in breaking all these bonds, which comes under the 1 mole. Then that heat, total heat required to break all HH bonds in 1 mole, that is called heat of atomization or enthalpy of atomization. Whenever 1 mole term is used, you think that in 1 mole means Avogadro number. In that number molecules are present, and that molecules collectively we are telling 1 mole. Okay, just like 1 ton, see, big quantity, 1000 kg, that is equal to 1 ton. Again you want to think in term of kg, then see how much kg is there. Then like that way, heat requires to break the HH bond, all bonds present in 1 mole, all bonds present in 1 mole. That heat is called heat of atomization or enthalpy of atomization. Example I have given you, H2. It is giving H2 gaseous, H2, but all should be in gas. H2 already is in gas, and when it will break, it will give 2H. Then this when it will convert into the 2H, that time it required 435 kilojoule per mole. Then this is called heat of atomization or enthalpy of atomization. Okay, then it is the enthalpy change on breaking 1 mole of bonds completely to obtain atom in the gas phase. In case of diatomic molecules like H2 or dihydrogen, okay, the enthalpy of atomization is also the bond dissociation. Another term is bond dissociation. Both are same. The enthalpy of atomization is the bond dissociation enthalpy. Both are same. The other example of enthalpy of atomization can take as a CH4 gas, methane gas. After absorbing heat, it will break into carbon atom and hydrogen atom. It will give 1 carbon atom, that is a gaseous phase, and 4 hydrogen also in gaseous phase. That time it requires 1665 kilojoule per mole. 1665 kilojoule per mole means 1665 kilojoule per mole. Okay. Products are here, you should understand that the products are only atoms of carbon and hydrogen in gaseous phase. Gaseous phase you have to not forget. Carbon and hydrogen both are in gaseous phase. Now third example you can take. Sodium solid, Na solid, that will convert into the Na gas. Na solid, sodium solid, it is converting into sodium gas, Nag. Then that time it requires 108.4 kilojoule per mole. Then this is also called atomization. In this case, the enthalpy of atomization is same as the enthalpy of sublimation. This is also because directly from without converting to liquid it is going to gas. Then that's why it is also called sublimation. Here both are same. In this case, in the case of sodium, that enthalpy of atomization is same as enthalpy of sublimation. Okay, that I have told you about enthalpy of atomization. Now I am going to tell about the very important concept, bond enthalpy. Bond enthalpy, that is a delta bond, bond, a small bond, you can write delta, and bond, a small letter, bond H. Okay, it is a symbol is delta bond H, capital H. Then what is the bond enthalpy? Bond energy, in simple way you tell bond energy. Okay, bond energy or bond enthalpy, or you can say these things, to break the bond, heat is required. To break the bond, heat is required. Okay, that is called bond enthalpy. Bond enthalpy, heat required to break the bond. Okay, what I discussed, that was these things, atomization. It came in the form of atom, correct? Now here you are talking about that breaking the bond. Okay, now listen, then you will understand the difference. Actually all are similar. Then bond enthalpy, you are giving the value of bond. Bond may be single bond, double bond, triple bond. Okay, then in breaking the bond, how much energy is required? Obviously single bond will require less energy, double bond more energy, and third triple bond very high energy. Okay, then here you are focusing on the energy required to break the bond. Okay, not to convert into ion only, not a atom, not the atom. Here you are focusing on the breaking of bond. Okay, chemical reactions involve the breaking and making a chemical bonds. This also you should understand. In any chemical reaction, what happens? Old bond will break and new bond will form. Rearrangement will take place. Okay, in any reaction, reactant, their bonds will break and it will give new things, that is the product. Then new bond will be formed. Here two things you have to understand: breaking of bonds of reactants, and that again it will give the product. Then they will form new bond. Then that's why it is called chemical reaction involve the breaking and making of chemical bonds. Energy is required to break a bond, and enthalpy and energy or enthalpy, whatever want you can tell, and energy is released when a bond is formed. Already I told you, when bond forms or molecule forms, then energy is released. Energy is released, heat of formation or enthalpy of formation. Then in breaking of bond, heat is required, and when new bond is formed, then energy is released. Means energy is required to break a bond and energy is released when a bond is formed. It is possible to relate heat of reaction to change in energy associated with breaking and making of chemical bond. Here important things is that correlation, means you can relate. What you will relate? It is possible to relate heat of reaction, means enthalpy of reaction. Heat of reaction you want to correlate to change in energy associated with breaking and making chemical bonds. Correct? You are going to correlate. We are going to relate heat. You are going to relate heat of reaction to change in energy associated with breaking and making chemical bonds. By example, you will understand. With reference to enthalpy change associated with chemical bonds, two different terms are used in thermodynamics. What are that two terms? Then first is bond dissociation enthalpy, and second mean bond enthalpy. Mean, MEAN, mean bond enthalpy. These two terms are used. Okay, then now understand these two. Both are telling about the same thing, but difference is there. Minor difference is there. Then you will understand. Now just try to understand. Let us discuss these terms with reference to diatomic and polyatomic molecules. Diatomic means only two atoms. Molecules has two atoms. Polyatomic means more than two atoms. Okay. Then in both cases we should understand. First to understand diatomic molecules. Then consider you can say this S2, what I have discussed. S2 molecules means dihydrogen. Consider you can say dihydrogen, in which the bond in 1 mole of dihydrogen gas are broken like that. S2 is giving 2H. Already I told you, and delta H that is equal to 435 kilojoule, 435.0 kilojoule per mole. Already I have told you during atomization. Same thing is here. The enthalpy change involved in this process is the bond dissociation enthalpy of HH bond. HH means hydrogen bond. Actually, dissociation, H2 is dissociating means bond is breaking. HH bond is breaking. Correct? And it is converting to atoms in gaseous phase. Okay. Then this is also called bond dissociation energy. The enthalpy change involved in this process is breaking H2 into 2H. In this process is the bond dissociation energy of HH bond. The bond dissociation enthalpy is the change in enthalpy when 1 mole of covalent bonds, 1 mole of covalent, actually HH has covalent bond. When 1 mole of covalent bonds of gaseous covalent compound is broken to form products in the gas phase. Both should be in gas phase. Okay, then bond energy and atomization both are same. Now again important thing. It is the same as the enthalpy of atomization of dihydrogen. Both atomization and dissociation both are same. This is true for all diatomic molecules. In the case of diatomic molecules, it is true. Okay. As for example, in case of chlorine, Cl2, it will give 2Cl. After the breaking, it will give 2Cl, gaseous phase. That time, that delta C, actually bond dissociation energy or bond energy is shown by delta you are writing, then below that HH you can write, or Cl you can write, or O you can write. That is telling about the bond, focusing about the bond. Okay, for each reaction some special sign is there, that automatically you will understand. H2 means we are talking about the bond, then H you can write, bond energy. Okay, Cl, delta you are writing, and below that a small h means H you write, Cl you write, O you write, then it is talking about the bond energy. Okay, bond energy. Then in the case of chlorine, it will give 2 atoms of chlorine in gaseous phase. Always you write you can say G, near the chlorine, a small g, near the chlorine atom also G. And heat, how much heat is required? Then delta H is equal to 242 kilojoule per mole. And in case of oxygen, it will give you 2O in gaseous phase, and that time delta H means heat of these things, bond energy will be 428 kilojoule per mole. Then bond dissociation energy and atomization are same in case of diatomic molecules. But now you can see differences. In the case of polyatomic molecules, bond dissociation enthalpy is different for different bonds. Here it is a minor change is there. Okay. Then in the case of polyatomic molecules, bond dissociation enthalpy is different for different bonds within the same molecules. Okay. Then now I am telling about the polyatomic molecules. Now you consider methane, CH4. Okay. Let us now consider a polyatomic molecules like methane, CH4. The overall thermochemical equation for its atomization reaction I am telling you now. Okay, CH4, first it will give directly CH4 gas. When its bond will break, it will give 1 carbon in gaseous state and 4 hydrogen in gaseous state. Gg you write a small letter in bracket. C gas plus 4H gas. And that time it will require 1665 kilojoule per mole. 1665. Already I told in case of atomization. But now here different you understand. Then CH4, 4 bond is there. CH. Then now these are the 4 bond. You will think all bonds may be equal. All bond, you may think that 4 CH bond is there, then it will require same type of energy to break the bond, all 4 bond. No. All 4 bond have different energy. It requires different energy to break the bond. Suppose first bond you are breaking CH, then it will require 427 kilojoule per mole. Okay, then it will give CH3 in gaseous state plus 1H gaseous state, and that time this bond energy will be, for this bond energy will be 427 kilojoule per mole. Now CH3 is remaining. Now again, if you can say second bond is breaking, then this time it will give CH2 gaseous state plus H, 1H, and this time it will require 439 kilojoule per mole, little more. Okay, for the second bond in breaking second bond. Now CH2 that will break, means third bond is going to be broken. Then this time it will give CH plus H, gaseous state. Then this time it is required 452 kilojoule per mole, again little more. Then for the all three bond, different in energy is required. Now last bond, CH is remaining, only one bond. Then it will give one carbon and one hydrogen in gaseous state. Then for this, bond energy will be 347 kilojoule per mole, less. Only in this case, again different, but less energy is required. Then here, if you will add all four bond energy, then it will become 1665, means total, okay, 1665 kilojoule per mole. And here bond wise means plus 427 plus 439 plus 450 plus 347. If you add, it will come 1665 kilojoule per mole. In such cases, we use mean bond enthalpy, mean MEAN, average, mean bond enthalpy of CS bond. Now you have understood that in the beginning we have used two terms, bond dissociation enthalpy and mean bond enthalpy. Now you have understood the difference. Then for the polyatomic, in case of polyatomic molecules, mean bond enthalpy is used, and for dihydrogen we are using bond dissociation enthalpy, and bond dissociation enthalpy is same as enthalpy of atomization. Okay, when bond breaks, then what will happen? Both will take one electron. Suppose single bond is there, and then both will take one electron, and it will convert into the atom, original atom. That's why it is called atomization. But same things you can tell in the term of bond dissociation also. Bond dissociated. I am talking about the, you can say, single bond, diatomic. Okay, equal the electron they will take. Then this I have told you about the, I think I can say, bond enthalpy. Again, you understand here these things more about this bond energy in case of polyatomic molecules. Then mean bond energy or bond enthalpy, how will you calculate? Mean bond enthalpy? Then 1/4, because 4 bond was there, 9 CH4. Then delta CH you can tell. Delta CH, carbon hydrogen bond. Then for this, delta H value will be for carbon hydrogen, that is 1/4 of total. 1/4 of total. Okay, that is the 1/4 of 1665 kilojoule per mole. That is it will come average, it will come mean it will come 416 kilojoule per mole. Okay. Then now one question might be coming in your mind. Why so much difference? Why they are differing in the energy? Bond energy, all are the equal bond, CH4. Then why it is different? This question might be coming in your mind. Then answer for this you can understand if you will consider the electronic configuration of carbon. Then you know that in before making bond, carbons are going hybridization. Actually, 11th student might be not knowing. I will discuss when I will start organic chemistry. But here you can know that carbon has 6 electron, atomic number 6. Then 1 s square, 2 s square, 2p2. This is the electronic configuration. Then 1 s square, they will not take part in bond formation because they are very strong, very high energy required to use this electron. Then 2 s square and 2p2, they are outermost, hence they can be excited soon. That's why only these 4 electrons can take part in bond formation. Then here this 2 s square and 2p2 go for hybridization. Then you know that p orbitals have 3 types. P has 3 types of orbital: px, py, pz. Already I have discussed in the beginning. Then in case of when I was just talking about the periodic table that time, atomic structure, that time I have discussed. Then P has px, py, pz, 3 orbitals. Then in hybridization, what will happen? Actually 2s square 2p2. Then already in p2 electrons are there. Then they will go. One electron will go in px, other electron will go in py. Third is vacant. Then after excitation, this 2s square electron, 2 electron is there. Then one will go for the py. Then now px, py, pz, one electron is there, and 2s, 1 electron is there. The total 4 orbitals are there. Then 4 hydrogen came and made 4 bond. 4 electrons are already were there with carbon. Now 4 hydrogen came with one electron and they made 4 bond. But now you can see 3 bond belong to the P and 1 bond belong to the S. Then you know that 3 orbitals px have 3 px, py, pz. Then one electron each they were having. They are stable. That's why they in that also px, py, pz, in broader sense we are telling they are equivalent, but they have little change in energy also. Okay, in broader sense all are equivalent energy. Equivalent is equivalent, not the 100% same. They have little change and there are differences, minor differences are there. That's why in breaking the 3 bond, they have got little difference. Not too much different, but they got little different. As for example, I told you that 427 in first bond, kilojoule required, other 439 and third 452. Okay, but little greater because when bond was breaking, one electron was remaining on carbon. Because bond breaking, then equally they have taken one electron. Then 1 electron was remaining. Due to that, some differences came. Okay, and fourth one it became less. Fourth one bond it required less. Okay, that is 347 kilojoule per mole. Why it is less? In other cases all were less differences. Here is a more difference. Why? Then here because fourth one bond belongs to S. They have used electron of S, 2s. Then they require less energy. Okay. P orbital have more energy, S orbital has less energy. That's why they require less. Actually these questions are asked only at a very high level, not for this, but in advance, IIT advanced they can ask sometimes in generally CSIR examination they will ask, Net examination. Okay, then that I have told you. Then how to calculate the mean? Then total divided by 4. Then you will get mean. Means it will come 416 kilojoule per mole. In objective question, multiple choice, they will ask this question. Okay, They want to know whether a student know about the mean or not. Mean energy. Mean, you can say this dissociation energy or enthalpy. Okay. Now, this I have told you about the mean CH bond enthalpy in methane. Okay. It has been found that mean CH bond enthalpy differ slightly from compound to compound. Again, important things I am telling you. Now, automatically you have understood that in other compound, it has been found that mean CH bond enthalpies differ slightly from compound to compound. As for example, in CH3, CH2Cl means ethyl chloride, CH3, CH2Cl, ethyl chloride, and you can say nitromethane. Nitromethane means CH3NO2, CH3, CH2Cl, ethyl chloride, CH3NO2, nitromethane. Okay. Then here Cl is attached, ethyl chloride, and nitromethane NO2 is attached. Then this chloride and NO, due to this chloride and NO2, that CH bond, CH3, CH2Cl, then 3 to 5 hydrogen bond is then a CH bond, CH3 3 bond, and CH2 2 bond, then 5 CH bond is there. Sixth one is CCl bond, CCl. Then due to this Cl, all you can say CH bond energy is different. Okay, CH3NO2 also same way. All CH has different bond energy. These are important things I have told you. Question is asked, and but I am telling you, but it does not differ in a great. Too much difference is not there. Using Hess law, bond enthalpies can be calculated. How will calculate bond enthalpies? Then by use of Hess law. Okay, again question is asked. Using Hess law, bond enthalpies can be calculated. Bond enthalpy values of actually this many all bond, many molecules are there, and they have single bond also, they have double bond also, they have triple bond also. Then there are many, you can say, values are there. For each bond, you know that different energies will be there for each bond. Then data are there, that is not required too much, but some values I will tell you, bond energy, which you should know and which question is asked. Then here one new things I am telling you, which you might be not knowing. Generally C double bond O, CO, C double bond O, CO, that is a common carbonyl group. What we are telling, carbonyl group. Then there you can say energy, mean you can say mean bond energy is 741 kilojoule per mole at 298 Kelvin temperature you have to mention. Generally it is at 298 Kelvin only. Then CO, that value all are knowing, and this CO is common. Okay, CO, C double bond, its value is 741. What is the new, and a student will not know, that is the C triple bond O. C triple bond O, it is not common, it is uncommon, and because it is a triple bond, its energy is highest, 1070 kilojoule per mole. All values are at 298 Kelvin. Then this is the highest, C triple O, triple bond O, 1070 kilojoule per mole. After that nitrogen come, N2, nitrogen gas, between the N and triple bond is there. You know that single bond has a less energy, double bond is more energy, triple bond is highest energy. Okay, in general. Then nitrogen they are asking. Okay, what I am telling you now, all question is asked. Then N triple bond. Its energy is 946 kilojoule per mole. That's why it is very stable, and this is called permanent gas. Bond is very stable. It will not break. That's why in air, nitrogen gas will be always there. Nitrogen gas, it is permanent gas. After that, after means first position we will call CO, that is the triple bond, that is the highest. Okay, keep aside, that is the uncommon. Now in common, nitrogen is 946, very stable, very stable. After that, it come second position is for CN, cyanide. C triple bond N, CN bond. CN triple bond is there. Then 891. Actually, you keep pen and paper with you. Important things at least you should note down. Okay. Then C triple bond N, 891 kilojoule, kilojoule per mole. And third position, that is a C triple bond, carbon triple bond, 837 kilojoule per mole. Then question may asking that they will give which one has I can say highest energy or a stable bond in which molecule. Then they can give these three options. Okay. Then these three you have to keep in mind because very strong. And C double bond, I already told you, that is the 741. Okay. Oxygen 498, O2. Okay, 498. And carbon double bond, that is 611, more stronger than oxygen. Carbon double bond is more stronger than OO, means oxygen gas. Correct? And carbon triple bond already told you. Then these things, important things I told you. And C double bond N, that is also called cyanide only, double bond CN, that is the 615 kilojoule per mole. Then this I have told you about the different can say energy, mean value, mean bond enthalpy, I have told you. Now one more relation I am going to discuss here, that is related to bond energy only. And I have the last video means just only last class video I have given one numericals also based on this formula. This is new and you should understand. Already I have told you that delta H means product minus reactant. I told you if you want to calculate heat of reaction, then product summation of all heat of, you can say heat of formation of all products minus summation of heat of you can say formation of all reactant. That formula I told you. Here you will find a little different. Means different means what? Here you are going to find reverse way. Only reactant minus product. There it was product minus reactant. Here reactant minus product, direct. Then what is this? Then this is heat of reaction. Heat of reaction has relation with bond enthalpies of reactant and bond enthalpies of product. Here actually what is the things? It is very conceptual, that bond is going to be broken. In this case, in bond enthalpy, when we are discussing during the reaction, first bond will break, reactant bond will break, and then a new bond will form during the reaction. When you are heating means you are breaking the bond, and then new bond will form, product will formed. Then here it is related to that. Then here delta H in this type of equation, in this type of case, delta H means heat of reaction, delta RH you can tell. Heat of reaction has relation with what? It has relation with bond enthalpy. Here using the term bond. There you were using the term that formation. Okay. Bond, there you were using the term that is the formation. Okay. Heat of formation or heat enthalpy of formation of product or enthalpy of formation of reactant, that you were using there. But here you are using bond enthalpy, means during the reaction what is going on, that you are considering here. Then bond enthalpy of reactant minus bond enthalpy of product, that difference is called heat of reaction. Means heat of reaction has relation with bond enthalpy of reactant and bond enthalpy of product. Means here when reactant is converting into the product during the reaction, means breaking the bond, making the new bond, breaking the old bond, making the new bond, then how much difference is going on of heat during this reaction, during the reaction. Here you are writing delta HR, heat of reaction. Then in this case it will be, you can say, summation sign bond enthalpy of reactants minus summation sign bond enthalpies of products. Okay, again I am telling delta RH standard, that all are the standard, delta H, that is delta HR means heat of reaction, that is equal to summation sign bond enthalpies of reactants minus bond enthalpies of products. Last class in video one numericals I have given. First diagram was only that. Okay, first numericals was that only. Okay, then understood the difference between that bond energy, that is the here in the what I discussed earlier, that was the related to formation, heat of formation of products minus heat of formation of reactants. That was the, you can say, delta HF. Delta H, delta means heat of formation of product minus reactant. But here it is the bond, BOND, don't confuse. Okay, then here the standard enthalpy reaction, that is the delta RH, is related to bond enthalpy of the reactants and products in gas phase reactions. In gas phase reaction, okay, generally in lab we will do in solution, but here this is applied in case of gaseous state. Okay, then this relationship is particularly more useful. This relationship is important, particularly more useful when the required value of delta F are not available. Actually, if heat of formation values are not available, that time this relation is very, very important. The net enthalpy change of a reaction is the amount of energy required to break all the bonds. Listen here, important things. The net enthalpy change of a reaction is the amount of energy required to break all the bonds in the reactant molecules minus the amount of energy required to break all the bonds in the product molecules. What I have told, same things. Okay, this relationship is approximate. This relationship is approximate and is valid when all substances, means reactant and products in the reaction are in gaseous state. Okay, then I have told you about the this bond energy. Okay, bond energy or bond enthalpy. This concept is very important. And now I am stopping only here. Next class again I will meet with some new terms. Okay, thank you.